Howdy, howdy, this is Mr. Potter. We're going to go over the 2015 free response questions on the BC Calculus AP exam in this video. So I kind of wanted to talk through these problems, maybe talk a little bit about where I think the points will be coming from, and kind of demonstrate how to do this one way or another. So we're going to start with problem number 1. So with problem number 1, it says the rate at which rainwater flows into a drain pipe is modeled by this function r. In cubic feet per hour, t is measured in hours, and we have a domain here. It says the pipe is partially blocked, so water flows out of this drain at a slightly different rate, and there are 30 cubic feet of water in the pipe at time t equals 0. So this 30 feet is going to become important later on. We're going to get to that in just a bit. Part A says how many cubic feet of rainwater flow into the pipe during the 8-hour time interval. So I have this rate here, r of t. And this is the rate at which water is coming in. So if I want to figure out the total amount of water that's come in over 8 hours, then on part A, what I want to do is find the integral from 0 to 8 of r of t dt. So I want to find the, let me get to my calculator mode. So I want to do the integral of, this is going to be 20 times the sine of t squared divided by 35. And I'm going to be integrating with respect to t from 0 to 8. And this will give me my answer, which is 76.570. And because they've been giving us units here, cubic feet per hour, and hours, cubic feet are our units for our volume here, and the units are going to be very important. So what the AP has typically done is if you fail to put units on one of your answers, you're going to lose a point for that, and then anytime that you lose that point, you're not going to be penalized again for it. But units are very important in this problem. So we're probably looking at 1 point for setting up the integral and 1 point for the value. This is what they've typically done. Again, I'm not an AP reader, but this is what we've seen on typical problems in the past, and so I would expect them to follow a similar practice here. For part B, it says that the amount of water in the pipe increasing or decreasing at time t equals 3 hours, and it wants us to give a reason for our answer. Keep in mind that water is being added at this rate, and water is being subtracted at this rate. So if I want to find the change in water with respect to time, it's going to end up being r at that particular time minus d at that particular time. So the change in water when time equals 3 is going to be r of 3 minus d of 3. And so if I evaluate that, I need to substitute 3 into this equation that we just had. So I'm going to backspace up, and I'm going to stick 3's in here. So 3 squared. And then I want to subtract this quantity, and this quantity is my d of t. So this is going to be negative 0.04 t cubed, but it's not t, it's 3. So it's going to be 3 cubed plus 0.4 times 3 squared plus 0.96 t, well not t, 3. And my parentheses are closed, so when I calculate this, we end up with this w prime being equal to, excuse me, let me get my calculator back up, being equal to 0.313 negative. And they'll accept credit for either the 0.313 or the negative 0.314. When the rounding occurs in this last spot, they'll usually give you credit for either or both of them. So don't worry so much about that. If you wanted to leave your answer as negative 0.3136, that would be fine. It gets rid of the ambiguity there. But what's important is that this is a rate, so this is cubic feet per hour. So it is going to be important for me to put those units on there. Then we get part C, and it says, at what time t, 0 less than t less than 8, is the amount of water in the pipe a minimum? Justify your answer. So I need to remember that minima occur at critical points and boundary points. So my boundary points are going to be at t equals 0 and at t equals 8. For my critical points, I want to know where w prime is equal to 0. and I need to figure out where those points are going to be. So I'm actually going to jump to my graphing part of this. I'm going to put y equals, and I'm going to type in my first equation, which is going to be 20 times the sine of, in this case, x squared, because I'm graphing y as a function of x, divided by 35 for my first function. I'm going to set up my second function to be the negative 0.04x cubed plus 0.4x squared plus 0.96x. And I want to know where these graphs intersect on my domain. Remember, my domain is from 0 to 8. And so if I graph this, so I see that something happens here at 0. I think I did something wrong here. Let me make sure I didn't do something wrong here, because that's not what the graph should look like. So give me my y equals. Okay. And actually, this intersection point is what I'm looking for right here. So I'm going to go math, so F5, and I want to figure out where the intersection is. And my first curve is that one, my second curve is that one, and that's my lower bound is going to be somewhere around 2, upper bound somewhere around 4. And so I find out that they intersect at 3.217. And the issue here is that it looks like they may intersect over here. So graphing these two lines may not be the best way to do it. What I may want to do is I may want to go ahead and let me actually cut this and then go up to my equation 1 and paste this. So minus this equation, paste, and have that be it. So this is really my r minus d that I'm dealing with. And if I graph this, then I can see, okay, it's decreasing on this interval, and then it reaches this intersection point here, somewhere between 3 and 4, and then this is increasing, and it tapers off, but it never actually, the derivative is never 0 again. So I'm going to go ahead and I'm going to go ahead F5 and find the intersection somewhere between 3 and 4. And I'll end up getting that exact same 3.27166. So this is going to happen at t equals 3.27166. So what I need to do is I need to figure out the volume of water at 0, the volume of water at 3.27166, and I need to figure out the volume of water at 8. Keep in mind that normally what I would do is I would be integrating from 0 to whatever time I'm dealing with of this r of t minus d of t with respect to t. And then whatever I get, I would have to add the 30 cubic feet that we started with at the beginning. Of course, here, this is just 30 because this integral is going to be 0. Here I'm going to have 30 plus the integral from 0 to 3.272 of r of t minus d of t. And when I put this in my calculator, going back to my home screen, I'm going to take this function and I want to take 30 plus the integral of this, and it's going to be all of this with t's instead of 3's. Would have been helpful if I'd changed these along the way. But I'm going to integrate this from 0 to that r value. And I'm actually going to put in all the decimal places that we got instead of just the 3 decimal places, just to make sure that my answer is as accurate as possible. So I'm going to integrate this with respect to t from 0 to 3.27166. And after a few minutes of repose, we get our answer of 27. And notice that this is significantly less than the 30 cubic feet that we had here. And then I need to evaluate this as at 8, so I'm going to take a step back and just delete this back up to an 8. And when we do that, we're going to get that's 30 plus the integral from 0 to 8 of r of t minus d of t dt, which is going to be 48.544. And so we have a minimum of 27.965 cubic feet at time equals 3.272 hours. And so that's what I'm looking for the solution. My justification is that critical points and boundary points are the only places where extreme I have, and this is the smallest value of our 3. So I'm showing my work here to kind of explain what's going on. And then part D says the pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow into and out of the pipe at the rates given until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So we've got this formula here that 30 plus the integral from 0 to whatever our time is of r of t minus d of t dt is going to be the amount of volume that we have. And whenever this volume hits 50, that's going to be the threshold point. Remember that when we were looking, at our graph, we noticed that let me go to our graph real quick. Our graph, this was positive, so this increase that we've got over here, the area of this means that we possibly could get up to 50 pretty quick. Remember that when we were at W of 8, we were at 48.544, and our derivative is still positive. So we're going to be continuing to add, and so we're probably going to hit that 50 threshold for this W. So I kind of stopped talking about the points. Let me go back to it. 2 points for part A. Down here, you're going to need some type of representation for the amount of water with respect to time, and you're going to need to have your answer for what happens at time t equals 3. You're going to have to identify some points, like the t equals 0, the t equals 8, the t equals 3.271, and you're going to be looking at a point to justify which one of these is your smallest. And then for this expression, you're going to have probably 1 point for this integral here and 1 point for finishing it out, writing it out as a equation. So this is probably where your 9 points are going to fall. Again, the one global point where if any point along the path you kind of messed up your units, then you're going to lose that point, but everything else should be fine on there. So we're going to move on to question 2. So scrolling down, question 2 says at time t greater than 0, a particle moving along a curve in the xy plane has position x of t, y of t, with velocity vector v of t equals cosine of t squared and e of 0.5t. And at t equals 1, the particle is at the point 3,5. A wants us to find the x-coordinate of the particle at t equals 2. So if I want to know the x-coordinate of the particle at t equals 2, I'm going to be using this information here, the x-coordinate when t equals 1, and I'm also going to be using this derivative information because this is really x prime of t. So I know that my position at time 2 has got to be equal to the position at time 1 plus the integral from 1 to 2 of my function, which is b cosine of t squared dt. So I'm going to jump over to my calculator real quick, and we're going to go to our home screen. And I want to figure out what x of 1 is, which is 3, plus the integral. And I'm going to be integrating cosine of t squared with respect to t from 1 to 2. And we're going to find out that x of 2 ends up being 2.557. And again, in this problem, I don't need units because there are no units here. So I don't need to worry about units in any of my question. I don't need to worry about hours or seconds or meters or feet or anything like that. So this is my horizontal position at time t equals 2. For 0 less than t less than 1, there's a point in the curve at which the line tangent to the curve has a slope of 2, and at what time is that object at the point? So for us, we know that the slope is supposed to be the change in y over the change in x. But because we're parametric, I'm really looking at y prime of t over x prime of t. So I want to know when e to the 0.5t over cosine of t squared is equal to 2. And so I want to look at when this is going to be true. And again, graphing is probably going to give us our best representation here. So I'm going to jump over to my graph. I'm going to clear this equation out. And I want to do e to the 0.5 x, because I'm graphing y as a function of x, divided by the cosine of x squared. And I want to know when this is equal to 2, so I want to graph the line minus 2. And I also want to change my domain because our domain's going from 0 to 1 in this problem. And what will happen is if you actually graph this, you'll see that this oscillates wildly past 1. So if I graph this function, I'm going to see where this actually intersects the x-axis. And it thinks it can, it thinks it can, it thinks it can, it thinks it can, thinks it can, right about there. So again, algebra is our friend. We want to find the 0 of this function somewhere between 0 and 1. And we end up with a solution of 0.840. So t equals 0.840. For part C, they wanted to find the time at which the speed of the particle is 3. So remember that speed is equal to the square root of x prime squared plus y prime squared. So when I'm looking for the speed and I want to know when it's equal to 3, I'm going to be solving the equation where I've got cosine of t squared plus e to the 0.5t squared. So I'm going to go back to the exact same graphing situation just to find that solution. So we're going to type in our equation again. So I'm looking at the square root of stuff, and it's going to be stuff squared plus stuff squared, and now I need to fill in my stuff. This first stuff is going to be cosine of x squared, and I need to close that cosine function. And I'm going to do the exponential, so this is going to be e to the 0.5x. And I like to put in the parentheses first before I start substituting in the values, because then I make sure that everything's balanced. And everything looks really good here. And I want to know when this is equal to 3, so I'm actually going to go back up here, go to the end of this, and subtract 3. Because I want to know when this is going to be happening here. And I don't know if that's going to happen in my domain, so I'm going to expand this out. Notice there's no mention of my domain here. So let's just type in any reasonable value. 5 sounds good. So if I graph this, then here is my... This is my speed graph. My speed ends up doing this. So this is where my speed ends up being equal to 3, somewhere between 2 and 3. So I'm going to go to my algebra and find the 0 somewhere between 2 and 3. And so I find out that my time is equal to 2.196. So this is the time at which my speed ends up being equal to 3. Then we get to part D, where it wants us to find the total distance traveled by the particle from time t equals 0 to time t equals 1. And I know that the total distance traveled by the particle, that's the arc length. So I want to find the arc length, the square root of, this is going to be x prime squared, so cosine of t squared squared, plus y prime squared, which is going to be e to the 0.5t squared. And I'm going to be integrating that with respect to t. So I'm actually going to jump back to my graph just for a second, because I actually want to copy this. So I'm going to hit enter, and I'm going to copy this expression, and then I'm going to go back to my home screen, and I want to integrate. So I'm going to do integrate, and I'm going to go ahead and paste this in, but I don't want that minus 3. And I want to integrate this with respect to x from 0 to 1. And when I hit enter, calculator thinks for a while. So the thing is, the distance is equal to, on part D, and this is equal to 1.595. Now again, on all of these that we had rounding, I could write 1.594 or 1.595, and they've given points for both of those, so just be aware that that's there. Again, if you always write 4 decimal places, then you should be good, because then you're writing something that is correct and is going to round to the answer that they have. So looking at the points on here, you're probably going to get 1 point for writing this fundamental theorem of calculus form and 1 point for your numerical answer. Here you're probably going to get a point for writing that slope is the ratio of y prime over x prime and 1 point for your answer. You're probably going to get 1 point for your speed equation, 1 point, or your speed function I should say, 1 point for setting it equal to 3 and 1 point for your answer. And then over here you're going to have 1 point for your arc length function and 1 point for your numerical answers. So I'm thinking that's where the 9 points are going to be separated on this problem. So we're going to go ahead and move on to question 3, and of course questions 3 through 6 are no calculator, so we're going to say goodbye to our TI emulator. So bye-bye. And we'll go ahead and scroll down a bit. So I've got this broken up into a couple of sections just so we can have space to write, but this problem is usually seen on the calculator portion, and so there are certain things that we see a lot. The first two parts we really don't need a calculator for. And it's usually not until we get to the modeling function, which is part C and D, where we would need the calculator. And I'll explain why we don't need the calculator when I get to those problems. So Joanna jogs along a straight path. For 0 less than t less than 40, Joanna's velocity is given by a differentiable function v given by this table. And part A says use the data in the table to estimate the value of v prime of 16. And you'll notice that there is no 16 on our table, but it does lie smack between 12 and 20. And I know that I can estimate v prime of 16 by looking at the slope between 12 and 20. So v of 20 minus v of 12 over 20 over 20 minus 12. Keep in mind this is an approximation. This is not the actual value. So when I approximate this, this is going to give me 240 minus 200 over 20 minus 12. Now, I'll tell you right now, number one, I'm lazy, but number two, you're not going to get any extra points if you simplify this. However, if you simplify it wrong, I guarantee you're going to lose points on this. What is very important here is that we are trying to estimate a velocity, and so we do need to make sure that we have our units, which is going to be meters per minute. And this is another one of those problems where you're going to need to put your units on all of your answers. So for part A, we're looking at this for our average rate of change, which is an approximation of our instantaneous rate of change. On part B, it says, using correct units, explain the meaning of this definite integral. Now, the thing that's important is the fact that we have absolute values here. And so this is not velocity, this is actually speed. And if I'm doing the integral of this, I'm integrating speed, which actually tells me the total distance traveled, because I'm going to be moving forward a certain amount, and then I'm going to be moving backwards an equivalent amount. So the integral from 0 to 40 of the absolute value of v dt represents the total distance traveled in meters from t equals 0 to t equals 40 seconds. So that's what it represents, and what I've accidentally cut off here is that it's asking for us to approximate this using a right-Riemann sum. So because I'm doing a right-Riemann sum, I'm going to be looking at the right endpoints, so the rightmost data values for the rectangles that we're looking at here. So I can say that the integral from 0 to 40 of the absolute value of v dt is approximately equal to, this first rectangle goes from 0 to 12, so this would be 12 minus 0, times the height of the rectangle, and we're using the right endpoint, which is 200. Plus my next rectangle, which goes from 12 to 20, so this is going to be 20 minus 12, and the height of this rectangle is going to be 240. Plus, this next rectangle goes from 20 to 24, so this is going to be 24 minus 20. And the height of this rectangle is not 220, it's 220. It's not negative, it's positive because of this absolute value. And then I've got my last rectangle, which goes from 24 to 40, so this is 40 minus 24, times the height of this rectangle, which is 150. And I'm not going to try and do anything more with this. This is perfectly well and good. This is simplified as far as I need to simplify it for the AP exam. I'm not going to waste time trying to make this more simplified. So that's part A and part B. So now let's take a look at part C. So for part C and part D, they give us a modeling function, and that's really what's different here. They give us a modeling function, and they tell us that Bob is riding his bicycle along the same path. It says for 0 less than t less than 10, Bob's velocity is modeled by this formula, where t is measured in minutes and b of t is measured in meters per minute. Find the acceleration. Now, normally this function's very complicated and we have to use a graphing calculator. That's why this problem usually shows up on 1 or 2. But because we're dealing with something that's just a polynomial, it's going to be very easy for us to take derivatives and antiderivatives because it's polynomial. So in this problem, remember that this is supposed to be a velocity function and they're asking us for acceleration, which means our acceleration is going to be equal to whatever b prime is. And so I need to take the derivative of this at 5. So I'm going to have t cubed's derivative is 3t squared, so that's going to be 3 times 5 squared. And, minus. This is going to be the derivative of 6t squared, which is going to be 12t, so 12 times 5. And 300 is a constant, so its derivative is 0. Now again, remember this is acceleration, so I need to talk about the proper units. Velocity was in terms of meters per minute, so the acceleration is going to be meters per minute squared. So for part C, this is as good as we need to get this answer here. And then we've got part D, which says, based on the model from part C, find Bob's average velocity during the interval from 0 to 10. Well, remember that this is a velocity function, so if I want to find the average velocity, then I'm going to have to use the 1 over b minus a times the integral from a to b of our function. This is t cubed minus 6t squared plus 300. So this is our average the average value of a function formula. It's really our fundamental theorem of calculus, because this is really antiderivative at 10 minus the antiderivative at 0 over 10 minus 0. That's really what we're calculating here. So the antiderivative of this is going to be t to the 4th over 4 minus, this is going to be 6t cubed over 3 plus 300t. And no, I'm not going to simplify this. The only thing I'm going to do is I'm going to put this 1/10 out in front, and I'm going to evaluate it from t equals 0 to t equals 10, and I'm going to substitute. So this is going to be, let me make sure I've got my equality here, it's going to be 1/10 of the expression, 10 to the 4th over 4, minus 6 times 10 cubed over 3, plus 300 times 10. And I would put minus and a whole bunch of other stuff, but substituting 0 into this polynomial gives me 0. So my average velocity is going to be this expression, and this is going to be in terms of meters per minute. So this is what we're looking at for part D. So now let's talk a little bit about points. Typically what we've done on part A, because that's dealing with the average velocity, the average rate of change to represent an approximation of the instantaneous rate of change, that's usually just a 1-point calculation. On B, we're looking for our explanation. So our explanation of that, including the correct units, is going to be 1 point, and our Riemann sum is going to be 1 point, so probably 2 points there. Then we have our acceleration, so recognizing the acceleration is the derivative and then actually substituting in the derivative points, that's going to be another couple of points. And then using the average value of a function, you're going to be probably a point for this and a point for the constant and limits and another point for this. And again, with the idea that because we're dealing with units, that 1 point is going to be dealing with units throughout the problem. So that's our 9 points for this problem. Right, on to problem 4. So on problem 4, we have our slope field, and we haven't seen a slope field for a while on a free response, but it is still an essential concept. One of the things I like to tell my students when they're doing these slope fields is to actually write the number of the slope out by each of these points and then try and draw your lines. So over here, I'm doing 2 times the x-coordinate minus the y-coordinate, and at these points x is 0. So really it's just the opposite of the y value. So this is going to have a slope of 1, this is going to have a slope of -1, and this is going to have a slope of -2. Over here, when x equals 1, it's going to be 2 times 1 plus these. So it's basically going to be twice as high as these. So they're looking at a slope of 0, a slope of +1, and over here a slope of +3. The other thing that's important to know when we're dealing with slope fields is that it's not necessary that you draw something that's exactly a slope of 1 or exactly a slope of 3, but that there's a obvious, clear difference between those. So when I'm looking at a slope of 1 and I'm looking at a slope of 3, the 3 should be sizably steeper. This 1 over here should be about the same slope that this one was. And this negative 1 should be about the same angle, just going downhill instead of uphill. And this 2 should be steeper, again going downhill. A 0 slope should be a horizontal tangent line. And so our slope field should look something like this. Again, we're talking about relative slopes. We're not talking about absolute slopes. So it's important that certain slopes go downhill and certain slopes go uphill. It's important that steeper slopes be steeper. But in general, these have usually just been 1 point. So I'm not expecting anything more than a 1 point. It's basically going to be an all or nothing type thing on this problem. For parts 2 and 3, we're going to be dealing with this differential equation. So for part B, it says let d squared y over dx squared be in terms of x and y. Well, I know that what we're looking for is we're looking for the change with respect to x of dy dx. So I'm looking for the derivative of 2x minus y with respect to x. So for us, that's going to be 2 minus dy dx. And this would be fine, except they do tell us to put it in terms of x and y. So this is going to be 2 minus dy dx, which is this expression. So 2x minus y, and I'm going to distribute this negative because we're going to need it later. So it's going to be 2 minus 2x plus y. And so that's what our second derivative is equal to. And then they say to determine the concavity of all solutions for the given differential equation in quadrant 2. Well, when I'm looking at quadrant 2, I know that all the points here have a negative for x and a positive for y. So in quadrant 2, what happens is d squared y over dx squared ends up being 2 minus a negative number plus a positive number. So this is really 2 plus a positive, which is greater than 0. So d squared y over dx squared is greater than 0 because x is less than 0 and y is greater than 0. Therefore, we're concave up. And we're going to be concave up for all points in this quadrant because of this behavior, because my x's are negative, because my y's are positive. My second derivative is always going to be 2 plus the sum of positive numbers. So it's always going to be positive, and we're always going to end up being concave up. In part C, it says let y be f of x be a particular solution to the differential equation with the initial condition f of 2 equals 3. Do I have a relative minimum, maximum, or neither? And I need to look at the behavior of dy dx in order to know if we have a critical point or not. So dy dx at the point where x equals 2 and y equals 3 is equal to 2 times 2 minus 3, or 1. And that's not 0. So we're neither a max nor a min, because the derivative isn't a horizontal tangent line and it's not undefined. So because the derivative is equal to 1, which is not 0, we're neither a max or a min. And then finally, part D, it says find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So this was part C. In part D, if I know that y equals mx plus b, then my derivative is just going to be m. But I know that my derivative is supposed to be 2x minus y. So I have this equation involving m, x, and y. And I know if I look at the second derivative of this function, I end up with a 0 because I have a constant slope. But I know that my second derivative is equal to this expression, this 2 minus 2x plus y. And so what I've got here is I've got a system of equations that I have to simplify. And if I try and solve this using elimination, if I eliminate my 2x's and eliminate my 2y's, all that's left on the right side is 2. On the left side, I've got m plus nothing, so I know that m equals 2. So I've got one of my variables. So I'm going to substitute back into this equation here. I'm going to say that 2 equals 2x minus y, and this looks an awful lot like a linear relationship, which is what I was trying to find. The only thing I don't have is I don't have my terms in the proper place, and so I don't know that b equals negative 2. And I think actually stating that b equals negative 2 is quite important because it does say to find the values of the constants m and b. So I think you actually will get a point for saying b equals negative 2, and I don't think this will be sufficient. You'll probably get a point for writing m equals 2. You'll get a point for finding the derivative and specifying that it's neither a max or a min. You're going to get a point for finding the second derivative in terms of x and y. You're going to get a point for concave up and a point for your justification. And then the other point that we're looking at is probably going to come from the slope field that we have up above. So that's what I'm looking at for the points here. And then on to question 5. So question 5 was probably the quirkiest of the questions that we saw on this test, just because it seemed like they were asking a whole bunch of stuff about the same function over and over again. But there were slight subtle differences, and I think it's important to go over those. So on problem 5, it says, consider the function f of x equals 1 over x squared minus kx, where k is a non-zero constant, and we have the derivative function given to us. On part A, they're saying let k equal 3, so this is now our function. And if k equals 3, then it's important to note that f prime is really 3 minus 2x over x squared minus 3x quantity squared. It's going to be important because if we're looking for a tangent line, we're going to need to find the slope. So for part A, I know that y is going to be equal to 1 over x squared minus 3 times x. And no, I'm not going to simplify that. And my slope is equal to 3 minus 2 times x over x squared minus 3 times x squared, and no, I'm not going to simplify that. So my tangent line is going to be y minus my y coordinate equals my slope times the quantity x minus my x coordinate. And I'm going to leave my slope-intercept form to look just like that because I'm not going to get any extra points for simplifying stuff. So that looks beautiful to me. For part B, it says let k equals 4, so this is what we have. And it says to determine whether f has a relative minimum, maximum, or neither at x equals 2, and justify our answer. So now our slope is going to be the exact same formula, except these constants are 4s. So my derivative at x equals 2 is going to be 4 minus 2 times 2 over 2 squared minus 4 times 2 squared. And I actually do have to simplify that, but it's not going to be a problem because 0 is my numerator. So the thing is, I do know I have a critical point at x equals 2, which means there's a good reason to think that we have relative extrema at this point. But in order to test this, I'm probably going to need to look at the second derivative. So looking at the second derivative, it's going to be the denominator, x squared minus 4x squared, times the derivative of the numerator, which is negative 2, minus my numerator, 4 minus 2 times x, and times the derivative of the denominator, which is 2 times x squared minus 4x, to the first times the derivative of what's inside, which is 2x minus 4. And this is all over my denominator squared. Now what's important to note is that for us, this term is 0, and so all of this is going to go away. So my f double prime evaluated at 2 is actually going to be equal to 4 minus 2 times 4 squared times negative 2 over 4 squared minus 4 times 2. 2 squared minus 4 times 2 to the 4th. But this is positive, this is positive, this is the only term that's negative, and so because I'm concave down, x equals 2 has a relative maximum. So I used the second derivative test. I envision that you probably could use the first derivative test, but you need to be pretty clear in showing that because number lines are not sufficient in and of themselves. You're going to have to do a little bit more explaining. So even though I had to do more math, I was kind of blessed because all of this is going to turn out to be 0 just because it's equal to what the numerator was before times stuff, and multiplying is not going to make it un-0. For part C, it says find the value of k for which f has a critical point at x equals 5. So now I know that f prime is got to be k minus 2 times negative 5 over x squared minus, or actually I should say negative 5 squared minus k times negative 5 squared. And I know that critical points happen where the function equals 0 or where the function is undefined. So if the function is equal to 0, I've got k plus 10 equals 0, and so k equals negative 10. And where the function is undefined, I'm going to have 25 plus 5k equals 0, and so k equals negative 5. The one thing I do have to be wary of is I have to make sure that these points are actually in the domain of my function. Now my function is this function up here, and I actually need to see what's happening when k equals negative 10 or when k equals negative 5. So for my function, f of negative 5, because that's the point in question, is going to give me 1 over negative 5 squared minus negative 10 times negative 5. And that should be well defined. But if I try and evaluate f at negative 5 for this one, I get 1 over, this is going to be negative 5 squared minus, it's going to be negative 5 times negative 5. And this is going to be 25 minus 25, which is 0. And so this is undefined. So the only point that's going to work is this k equals negative 10. The k equals negative 5 isn't going to work for me because it's not part of the domain of my original function. So that's our work for part C, and then we get to part D. It says let k equal 6, so we get 1 over x squared minus 6x. Find the partial fraction decomposition for the function f, and then they want to find the antiderivative of f of x. So we're going to start with our partial fraction decomposition. So I know that 1 over x squared minus 6x has got to be equal to some constant over x plus some constant over x minus 6 because the denominator factors that way. So I end up with a times this x minus 6 term that it's missing. So I'm going to have ax minus 6a. And over here, b is missing the x term, so that's going to be bx. And over here, I've got a constant of 1. I don't have any x's. So I end up with a plus b has to be 0, and negative 6a has to be 1. So a is negative 1/6, and b equals 1/6. So what I've got here is 1 over x squared minus 6x is really equal to negative 1/6 of 1x plus 1/6 of 1 over x minus 6. And so this is what I'm going to end up integrating. So when I integrate that negative 1/6 is a constant, it can come out, plus the 1/6 is a constant, it can come out of 1 over x minus 6 dx. And so this is going to give me negative 1/6 natural log of x plus 1/6 natural log of x minus 6 plus a constant. So this is my antiderivative down here, the integral of f. And I don't need to simplify this the way I would need to simplify this for a multiple choice question. This is a beautiful answer. And it's something that's really important to realize is that you're not going to get any points for simplifying. You're not going to get any points for evaluating once you've gotten all the calculus done. You're only going to lose time and possibly points if you make a mistake. So just please be careful when you're doing this. Looking at points, I'm envisioning that you're going to get a point for a y value and a point for a slope on here. That's going to be your equation of your tangent line. Over here, you're going to get a point for deciding you have a critical point at x equals 2. You're going to get a point for your answer with justification. your justification is either going to be a first derivative test or a second derivative test. Over here, you're going to get a point for coming up with any number of k's that include k equals -10, and you're going to get a point for confirming that k equals -10 is your only critical point. And then over here, you're going to have a point for your partial fraction decomposition. I know you're going to get a point for the actual answer over here. And we're going to get another point somewhere around here. Let's just say that you actually get a point for writing the entire tangent line. Because I imagine the first three parts here are probably parts on your AB test as well. We need to get those AB kids some points as well. So on to question 6. On to our Taylor polynomial, Maclaurin polynomial, power series, fun stuff. So the first thing we have to do on problem 6 is we have to come up with a ratio test to determine the radius of convergence of this function. So remember that when we're doing the ratio test, we're looking for the limit as n increases without bounds of the absolute value of a sub n plus 1 over a sub n, and we want to know when this limit is less than 1. So for our purposes, I'm going to look for the limit as n increases without bound, and I'm going to substitute n plus 1 for all of these terms. So I'm going to have -3 to the n, x to the n plus 1 over n plus 1. And because I'm dividing by something that's going to be a fraction, I'm going to multiply by the reciprocal. So -3 to the n minus 1 times x to the n, and in the numerator I'll have an n. So continuing to simplify this, this will actually divide out with all but one of these terms, as will this. And so I'm going to have the limit as n increases without bound. This is going to be -3 times x times n over n plus 1. And these terms have absolutely nothing to do with n, so I can take them completely out. And also, because we're inside absolute values, I really don't care about that negative sign so much. So I've got absolute value of 3x times the limit as n approaches infinity of n over n plus 1, and this limit ends up being the big old 1. So I've got 3x in absolute values, and I want to know when it's less than 1. So because the absolute value of 3x has to be less than 1, x has to be less than 1/3, the absolute value that is. And so my radius of convergence is equal to 1/3. So that's part A. On part B, it says write the first 4 non-zero terms of the Maclaurin series for f prime. So we're going to be taking the derivative of this function here. So I'm looking at this function. I've got x minus 3/2 x squared plus 3x cubed. So f prime is equal to 1, because that's the derivative of x, minus 3x, because the 2 will cancel out that 2, plus I'm going to have 9x squared. And if I look at the next term, remember this was really 9x cubed over 3. They just did some simplification. The next one's going to be 27x to the 4th over 4, so this is going to be minus 27x cubed plus my dot dot dot. And one of the things that I notice here is that this is a geometric sequence, where my first term is 1 and my common ratio is -3x. And that's important because we're looking for a rational function to represent this. And I know that the sum ends up being the first term over 1 minus r, which for us would be 1 over 1 minus -3x. So that's really 1 plus 3x. And this is a wonderful representation for f prime. And of course, it was important for me to make sure that I put the first 4 non-zero terms of this. I put equality because the sequence does continue, but these are the first 4 non-zero terms here. For part C, we're dealing with the first 4 non-zero terms of the exponential Maclaurin series. So I know that e to the x is equal to the sum of x to the n over n factorial as n goes from 0 to really, really big. So this is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus stuff. So there's my first 4 terms. And now I need to write a third degree Taylor polynomial for g of x. So g of x is supposed to be e to the x times f of x, where e to the x is what we just put. So x squared over 2 factorial, x cubed over 3 factorial. And there's going to be stuff here, but none of this stuff is going to contribute to a third degree Taylor polynomial. Only third powers and less will contribute. And this is going to be times x. So I'm going to have x minus 3 halves x squared plus 3x cubed plus stuff. And again, only stuff up to the third power are going to contribute to a third degree Taylor polynomial. And I'm just going to distribute 1 times all of this stuff. Well, 1 times x is x. 1 times 3 halves x squared is 3 halves x squared. 1 times 3x cubed is 3x cubed. And 1 times any of these higher order terms are going to be beyond the third degree that we're looking for. So now I'm looking at the next term, x times all this stuff. Well, I'm going to have x times x, which is x squared, x times 3 halves x squared, which is going to be 3 halves x cubed, and x times anything third power or bigger is going to give me a fourth degree term. And then I have my last term here, x squared times stuff. So x squared over 2 times x is going to be x cubed over 2. And if I do x squared times x squared, that's going to be too big. X squared times any of these other terms. And x cubed times any of these other terms is going to be too big. So this is it. This is the third degree Taylor polynomial. And I could simplify it. I could combine like terms, but I don't see a purpose to. It's not even going to try and simplify to anything nice if I look at this, so I'm going to leave it like this. So again, looking at points, you're going to get a point for trying the ratio test, and you're going to get a point for doing the ratio test successfully, and then 1 point for your final answer for your radius of convergence. You're going to get 1 point for your, let's say, your even power terms, and 1 point for your odd power terms or your negative terms, however you want to say it, and 1 point for recognizing the geometric sum. And then you're going to have 1 point for your Taylor series for e to the x. You're going to get 1 point for probably trying to distribute this out, and 1 point for getting the proper product of terms. So this is what I'm looking for the free response. Again, I'm not an AP reader, I'm not an AP grader, and so I'm just kind of giving my eyeball of where the points should go. And I'm certain that I've made mistakes along the way, so if you've made mistakes, if you can go ahead and leave a message down in the comments. I'll probably put a message on the video if I find any. But I do appreciate you watching. Hope you had a wonderful year of calculus. Once again, this is Mr. Potter. Thank you for watching. Have a great day.